Okay, so what we're going to do here is use potential energy G to get the discrete finite element equations, KD equals F. So this is a little more general approach to doing this. Actually, a better way to do this, well, not better, but a different way to do that, it's a little more general, is actually the method of weighted residuals, or finding a weak form. But for this class, actually, this isn't a bad approach because you got a good feel with potential energy. So again, just to look at the problem we're considering. So we have this computational domain, omega, right? Its boundary is broken up into two parts. One part where we have essential boundary conditions prescribed with the displacement, and then another region where traction is prescribed, traction vector is prescribed, and I'm going to call that gamma t for traction, gamma u and gamma t. All right? And every point has to belong in either one of those other domains, and there can be no overlap. All right. So we want to find the displacement field on this domain omega such that the total energy of the system is minimized. So what I mean by that is, well, it kind of makes sense. I mean, there's an infinite number of solutions. You can pick out the different displacements, but the one that minimizes the total energy is the solution. Okay, this is sort of a principle of least action, if you will. And we're going to define the total energy as equal to the internal strain energy, I'll call that U internal, minus the work done by the external forces. Okay, so that's the tractions or the external forces. This is the strain energy. All right, so let's break this up. So the strain energy is, well, it's an integral quantity over the whole domain. So we're going to look at the strain energy at every point, integrate it over the whole domain. That's the total strain energy. And for an elastic body, we're going to define the strain energy as 1/2 strain contracted with stress. Okay? And so for those who have seen this sort of stuff, this is basically like force times distance, if you will, but per volume. Okay? So if you think about it, the stress is a force per area. The strain is a change in length over a length. So here we have a force times a distance, that's a work, and there's a length times an area, that's a volume. So this basically gives us the work or the energy per volume. Okay, it's the strain energy per volume. All right, and we're going to look at that over the whole domain. And the 1/2 is here because it's a linear system, and it's very similar to, if we have proportionality here of Young's modulus, it's the area under the curve, right? Okay, it's like Hooke's law, or strain energy of a spring. All right, now when we do this, I'm just going to consider for now 2D stress states. Plane stress, plane strain, okay? And in that case, we can write this strain double contracted with the stress as follows. The strain component's written in a row vector, okay? The normal, and then the engineering shear strain dotted with the stress components in a column vector. So that's sigma x, sigma y, and then tau xy. So those are the work conjugate components. All right. And if you look at that, if you write that out, you can see what that gives you. That gives you the dot product of that, if you will. Okay, that's the total energy. Okay. All right. Now, we know that we can, this is what we used to write as the sort of the strain vector, but transpose the column vector on its row. And so this we know is B times D transpose, right? And so that gives us, it's just you flip them and you get the transpose of each. So this term here is actually going to just be D transpose. It's the row vector times B transpose, okay? Now likewise, this stress in Voigt form we can write as the material stiffness matrix C times the strain, and the strain we can write as B times D. So this gives us C times B times D, if you will. All right? Okay. So now I have that the internal energy is equal to the integral over the domain, omega, of 1/2 this D as a row vector, B transpose C B D omega, and those I've read in the book start to see something familiar here, right? Oh, and I forgot a D. Times D omega, all right? Now, if you look at this, these D's are nodal values. They're constant. They don't vary with respect to position. They can come out of the integral. This B matrix is a function of position, and in general, C could be a function of position, but often it's not, okay? But we'll assume it is, so that stays in there. All right, so let's slide our page up a little bit, make sure everything stays on there. And now what do I have? So pulling those things out, I have that the internal strain energy is equal to 1/2 D transpose. Now we're going to integrate over the domain. B transpose times C times B times D omega times D. Okay? This term here is going to turn out to be exactly our stiffness matrix, K. Right? Okay, now going back to the energy argument, it's not minimizing the internal energy, it's the total energy. So we need to come to terms with this external energy. So if you think of the external energy, this is the work done by these tractions, okay? So this external work, again, well, we're going to integrate over the region where the tractions are defined. So that natural boundary, that traction boundary condition, gamma t, okay? And again, we're going to consider just 2 dimensions, so we can write this as, well, the simplest way to think of it is the work is the displacement dotted with the traction. Now this is surface integral, so I write it as d gamma, okay? All right. So kind of putting this into matrix form, and considering that it's 2D, this is the displacement in the x direction, displacement in the y direction as a row vector, traction in the x, traction in the y. And these might be functions of position, right? These are definitely functions of position. That's the interpolation. All right. Now let me look at this a little bit. So this is what comes about from our finite element interpolation. All right. So I'd like to get this in something in terms of D and the shape functions. So let's look at the following quantity. Let's do it this way. Well, before we do that, let's look at this. If I write a well, let's not do that. Excuse me here, right? Let's get it the right dimension. If I look at the nodal displacement vector, right? U1, V1, U2, V2 to UN, VN. You can't see that, it fell off the page, okay? This is our column vector of nodal unknowns, D, right? So those are the degrees of freedom. And they're usually grouped in this manner, right? By node, and then the degrees of freedom per node, okay? I want to get this to look something like this. I want to get the U displacement and then the V displacement in a column vector, all right? Basically, it's this term transpose, right? Okay, so what matrix are we going to multiply by? Well, it has to be something that has 2 rows and then this 2 times n columns, okay? Now, this top row gets multiplied by the displacement vector and should give me the u's. Well, we know that this needs to be the ni's times the nodal unknowns, the x nodal unknowns. It only involves the x degrees of freedom. So everywhere you have the y's, it should be 0. And everywhere you have the x's, you should get the shape function. So it should be something like this. n1 of x times 0, and then 0. And then n2 of x and 0, and then so on and so forth until you get nx of x, and then in here is a 0. I didn't leave myself enough room. I'll rewrite it. Likewise, this bottom row is what gives you the y degrees of freedom, so everything involving the x's should be 0. You get 0 and 2, right? So that's really bad. But I'm going to call this matrix NV transpose. It's something like the shape function row vector, but it's such that it gives the displacements of the vector field. So I have the little v there. So what I really mean by this is, let's do it this way. I'm saying that NV is written as follows. I'm going to write it a little more neatly. N1 of x, 0, 0, N1 of x. Okay, that's not that neat. N2 of x, 0, 0, N2 of x. So on and so forth until we get to N of x, 0, and then 0, and n of x, the last shape function. All right? So it has this diagonal form, and if you had 3 dimensions, you'd have 3 degrees of freedom per each block. You'd have n1, 0, 0, 0, n1, 0, and then 0, 0, n1, right? So this is what I'm going to call NV, all right? So I can actually write U of x, V of x, what I have up here, that I can write as D transpose times NV, all right? And you can see the dimensionality that works out, right? This is a 2n by 1, and this is a 2n by 2, and then that's going to get dotted or contracted with the traction vector, which is a 2 by 1. All right, so the dimensionality works. Okay, so now that gives me the internal force, finally. I'm sorry, the external force, the energy of the external force, external, is equal to the integral over the whole domain. I'm sorry, not over the whole domain. Oh, I'm sorry, I'm really screwing up. Integral over the traction boundary, right? Just this boundary, not the whole domain. And it's D transpose times this NV matrix, and then that's going to be multiplied by the traction vector, x and y. And those, in general, are going to be functions of position, okay? Now this is a constant, it can come out, and so we just are left with d transpose integral over gamma t of this NV matrix multiplied by the tractions, d gamma, okay? So that's the work of the external forces. We have the work or the energy of the internal forces, okay? So now I can write the whole thing. Actually, I don't want that one. This is the one I want, right? Right? Here's the total energy. Here's the internal energy. Here's the external energy. So this is going to give us, let's just slide this up here. U total, okay, the internal energy, 1/2 d transpose. Well, okay. Yeah, okay, I'll leave it in here. Omega. Yeah. B transpose C B d omega times the displacement vector minus d transpose times the integral over the traction boundary condition, and V, just call this T, that's the traction vector, d gamma. All right? So now that is the total energy of the system. Now the question is, find the displacement field such that this is minimized. All right. Now, in this problem, I've already introduced the finite element interpolations. So what was once like an infinite set of values, spatially, right? You had an infinite dimensionality there, right? At every point. You know, this is now, if you think of it, looking at all possible displacements is the same now in the discrete sense at looking at all possible values or combination of values for the nodal unknowns, the U1, V1, U2, V2, so on and so forth, okay? So we want to minimize this with respect to these. This is one equation. If you look at this, this is a single equation with 2n unknowns. The two n's are where n is the number of nodes, and you get 2 degrees of freedom for each node. So there's 2n unknowns. That's D, right? You get one equation. That doesn't do you any good. But if we look at taking the derivative of U total with respect to di, where I is one of those degrees of freedom, and set that equal to 0, that's finding the extremal point. This is now going to give me 2n equations that I can solve for the 2n unknowns. Okay? So that's what we're doing. That's how we're minimizing. We're just looking for the stationary point or the extremal point, right? So it's just that simple. Now we just need to do the differentiation. Another way to write it, I'll do it quick because I know I've got a little long in this, but another way you can think of writing this is as follows. And here I'm just going to write D as a vector. All right. Now if you look at this first term, you basically have a D squared here. Okay? All right. So that acts like a D squared. So you get a 2, cancels out the 1/2, and then you're just left with the integral over omega B transpose times C times B d omega, this quantity, multiplies by D, right? That's what's left after you square it. You take the derivative of the squared. Now the second term, okay, you just have the single d. Okay, so you take the derivative that drops out, and you're just left with integral over the traction boundary condition of this NV matrix times the prescribed traction. And this we're going to set equal to 0. And actually, I should put braces around that because, well, it's not the null set, it's the a 0 column vector. All right. And now this, if you look at this, this looks something like where a stiffness matrix should go. This term here is the external force vector. And now this gives me K times D equals F. So this minimization gives me KD equals F, where K is defined as follows and F is defined as follows. So what that means is for any element where we can write the B matrix, and then we can write this NV vector, and then given a prescribed traction, you can integrate over the element and come up with the stiffness matrix and also the external force vector. You don't have to worry about doing this sort of ad hoc approaches like sum of forces at the nodes like we did for the bar element. Okay? So that's where those equations come from in the book.